In this video, we will learn about Big M method. This method is very useful in getting initial basic feasible solution table for such linear programs where it is not easy to get a basic variable from the constraints. We have seen in earlier video that if the constraint is less than equal to type, we make it equal to by adding a slack variable. This slack variable remain present in only that equation, and since these slack variables are nowhere else, so they immediately qualify to be a basic variable in the simplex table. But if the constant is of greater than equal to type or equal to type, then we don't get a basic variable from these constants so easily. In that case, we have different methods to get initial basic feasible solution table. Big M method is one of them. We take a very general linear program here. Since we have dealt with maximization problem earlier, so we will be taking a minimization problem here. And the constraints we will have less than equal to type, greater than equal to type, and equal to type. So all the three possible types of constants we will be keeping in this problem. And the decision variables too, we will have all possibilities like greater than equal to 0, less than equal to 0, and unrestricted. So let us take a problem of that kind. We will be preparing an initial basic feasible solution table to solve this linear program, where the objective is to minimize z equal to 10x1 minus 20x2 plus 5x3. So this question is of minimization type, not for maximization. Subject to constraints 35x1 plus 50x2 minus 10x3 greater than equal to 200. 10x1 minus 15x2 plus 20x3 less than equal to 400. Minus 2x1 plus 10x2 plus 25x3 equal to 150. So we have all the three types of constants here: greater than equal to type, less than equal to type, and equal to type. And the decision variables x1, x2, x3. x1 is greater than equal to 0, that is non-negative. x2 is non-positive, it has to be less than equal to 0, and x3 is unrestricted, it can take any value. For the simplex method, it is necessary that all the decision variables are non-negative. But here we have x1 greater than equal to 0, but x2 and x3 are not meeting that criteria. So we'll have to do some substitution so that the decision variables become non-negative. x1 greater than equal to 0 doesn't cause us any problem, but x2 is less than equal to 0. If we make a substitution, something like say x4 equal to minus x2, then when x2 is less than equal to 0, x4 will be greater than equal to 0. So this simple substitution in the problem will convert this decision variable of x2 into another decision variable of x4, where x4 is greater than equal to 0 when x2 is less than equal to 0. This way we can get rid of this difficulty that a decision variable is less than equal to 0. Similarly, when we take x3 unrestricted, we can do a substitution something like this: x5 minus x6 equal to x3, where x5 is greater than equal to 0 and x6 is also greater than equal to 0. We can see that when x5 is greater than x6, in that case x5 minus x6 will be greater than 0. When x5 is equal to x6, then x5 minus x6 is equal to 0. And when x5 is less than x6, you find that x5 minus x6 is less than 0. x5 minus x6 is x3. So you find that x3 greater than equal to 0, x3 equal to 0 and x3 less than 0. All these possibilities are being taken care, that is x3 unrestricted. This condition can be satisfied by doing a substitution of x5 minus x6 equal to x3, and this takes care of all the possibilities of x3 greater than 0, less than 0 and equal to 0. In this case, x5 and x6, these two decision variables which we are introducing to substitute x3, these decision variables are greater than equal to 0. So if we make a substitution, x4 equal to minus x2 and x5 minus x6 equal to x3, then we will be getting all the decision variables which are non-negative, and that meets our requirement. So let us do the substitution and rewrite these equations or inequalities. Our objective function is minimize z equal to 10x1 is okay. For x2 we will be substituting minus x4, so we get plus 20x4. For x3 we will be substituting x5 minus x6, so we get 5x5 minus 5x6. Subject to the constraints 35x1, since x1 is already greater than equal to 0, so there is no change here, we will write 35x1 plus 50x2. For x2 we are substituting minus x4, so we get minus 50x4. This substitution because the variable x2 is less than equal to 0 type, and if we substitute x2 equal to minus x4, then for x2 less than equal to 0, x4 becomes greater than equal to 0. For 10x3 we have to substitute x3 equal to x5 minus x6, so you have minus 10x5 plus 10x6 greater than equal to 200. Second constant 10x1 plus 15x4 plus 20x5 minus 20x6 less than equal to 400. Third, minus 2x1 minus 10x4 plus 25x5 minus 25x6 equal to 150, and the decision variables x1 greater than equal to 0, x4 greater than equal to 0, x5 greater than equal to 0 and x6 greater than equal to 0. Thus we have a linear program where all the decision variables are greater than equal to 0. This we have got by doing proper substitution in the original problem. We have already handled problem where the objective function was maximization type. Here the objective is minimize. Now instead of learning altogether a different method and getting confused, it is better to stick to that maximization problem only, and that can be easily done by converting this minimization problem to maximization problem. As you know, here you are trying to minimize z. So let us substitute for z equal to say minus w. So when you minimize z, you are actually maximizing w, and at the end, suppose we maximize w and do this substitution w equal to minus z, then we will be getting the minimum value of z. So let us do the substitution and rewrite the problem. Another thing which we will be doing, that all the constants which we are having here, that is greater than equal to, less than equal to, we will convert them to equal to. Our target is to prepare an initial basic feasible solution table in this video, and if you recall the earlier video on similar topic, you know that the constants are to be made equal to by adding slack variable or by subtracting surplus variable or by some way. So let us do these two things together here, that is converting the minimization to maximization and putting all the constants in equal to form. So we do this here. Our objective function now becomes maximize w, which is equal to minus 10x1 minus 20x4 minus 5x5 plus 5x6. If we bring right hand side terms to the left hand side, then you get w minus, or rather plus 10x1 plus 20x4 plus 5x5 minus 5x6, and the constants (35x1 minus 50x4 minus 10x5 plus 10x6). Here the constant is greater than equal to. So since left hand side is greater than equal to, and you want to make this equal to 200, so you'll have to subtract something. So we subtract a variable s1, which is called surplus variable, and this is equal to 200. That is, the left hand side is equal to 200. For the second constant, that is 10x1 plus 15x4 plus 20x5 minus 20x6. Here the constant is less than equal to type. Left hand side is less than equal to 400. To make it equal to, we will have to add something. So we add another variable s2, and this makes the left hand side equal to 400. S2 is called slack variable. The third constant, that is minus 2x1 minus 10x4 plus 25x5 minus 25x6. This anyway is equal to 150. and x1 greater than equal to 0, x4 greater than equal to 0, x5 greater than equal to 0, and x6 greater than equal to 0. Now we are ready to prepare the table. So let us do it here. For preparing a table, you have to write all the variables which you are using in this program. So we start with W, x1, x4, x5, x6. We have introduced s1, s2, and we have right hand side values. And we will have basis in which first W line will be there anyway. And we need basic variables from the three constraints. And for that, you know that a basic variable is one which is present in only one equation. So if you look at the first constraint, that is 35x1 minus 50x4 minus 10x5 plus 10x6 minus s1, you see that only s1 is a variable which is present only here and not present in any other equation. But then it has to have the coefficient plus 1 if it has to be taken as a basic variable. Now if you try to make this coefficient, which is minus 1 right now, plus 1 by multiplying both sides by minus 1, then you will get plus s1, but then right hand side value 200 will become negative. And you know that for a feasible solution, right hand side values should not be negative. So multiplying by minus 1 is not going to help us. One way to get out of this problem is that we introduce one artificial variable. Artificial variable, say a1, which is artificial. It is breaking the rules of mathematics, but we just say that a variable is added here. It is just to get a basic variable. We are doing it forcefully. In this case, we get a1 as a basic variable. It causes a lot of inconvenience, though it is giving us a basic variable. It is solving our problem temporarily. But presence of artificial variable which doesn't have any mathematical meaning in the basis will cause a lot of difficulty. So we try to make such an arrangement that artificial variables, if they go out of the basis, they never come back, and we associate some high penalty, and that way we manage it. Right now let us continue. We will be taking a1 as basic variable from the first constraint. So we have a basic variable here, a1. From the second constraint, 10x1 plus 15x4 plus 20x5 minus 20x6 plus s2. This constraint was originally less than equal to type, and here you see that s2 qualifies for the basic variable. So we don't have any problem in getting a basic variable from second constraint. The third constraint, which is equal to type, here again you are not getting any basic variable, and to resolve this problem we add another artificial variable here, that is a2, and we take that as entering variable in the basis. We take that as a basic variable. So the third variable in the basis is A2. A1 and A2 are artificial variables, and though we can't do much to make them out of the basis, but we can do something so that if they get out of the basis, they never come back. First of all, let us write all the coefficient here in this table. In the W line, you have you for filling the W line, just look at the objective function which you have here, and so the coefficient of W here is 1, coefficient of x1 in W line, if you see, that is 10, so we write here 10. Coefficient of x4 in W line is 20, coefficient of x5 in W line is 5, coefficient of x6 in W line is -5, coefficient of S1 in W line is 0, S1 is not there, coefficient of S2, that is also 0, A1 and A2 are also not there. We can write 0, but we want to do something, so let us hold those coefficients here right now. Right hand side value is equal to 0. Then A1 line, if you see, the coefficient of W in A1 line is 0. In fact, if you do it quickly, you will find that the coefficient of W in all other lines are 0. Same way x1, if we take vertically, then coefficients are 35, 10, -2. Same way if you take the coefficients of x4, you get here -50, 15, -10. Same way for x5, you get -10, 20, 25. For x6 it will be 10, -20, -25. Coefficients of S1. S1 is in the first equation, and that is -1 coefficient, and it is not there in other, so 0, 0. S2 is not there in the first one, in the second one it is there, so 1, and in the third one it is not there. A1 is present in the first equation, so you get here 1, and then other equations 0, 0. A2 is present in the third, so 0, 0, 1. Right hand side values 200, 400 and 150. We are left with the coefficients to be filled for A1 and A2 here. And since we want that A1 and A2 never enters in the basis in future, so the best way is that since for entering variable we look for negative coefficient in the objective function line, here we put a very high positive value, positive coefficients for A1 and A2, which will never turn out to be negative whatever we do, and so A1 and A2 will never enter into the basis. By putting coefficients m here, we have again violated the rules of mathematics. As we know that basic variables A1, S2 and A2 should be present in only these equations and should not be present anywhere else. By putting m, you are making A1 and A2 present in the objective function line also. The coefficient of all the basic variables in the objective function line should be equal to 0. Since we are keeping here m, so obviously it is going against that rule. So we need to do some row operations so that we get 0 here, and rest other conditions also are met. For that purpose, let us try to find out one elementary row operation. Since you want 0 for this m, and in this column if you look at this, you have 1 here and 0, 0. So if you multiply this row by m, and then subtract from the original row, you will be getting 0. The same elementary row operation should bring this also 0. So we can look into this particular column. Here again you have a 1 and rest 2 zeros. So if you multiply this row also by 1 by m, and then if you subtract from here, then you will be getting a 0. So our elementary row operation could be that we multiply this row by m and we multiply this row also by m, add them, and whatever we are getting, that we subtract from the original objective function line. Let us see that we multiply the a1 row by m. So we are multiplying a1 row by m. So we get here say m into 0 is 0 plus 35 into m is 35m minus 50m minus 10m 10m minus m 0 m 0 and 200m. Same way we multiply a2 row also by m. So we get 0 minus 2m minus 10m 25m minus 25m 0 0 0 m and 150m. As a rule, you can take that wherever you have introduced artificial variables, these rows should be multiplied by m. They should be added, and whatever result you are getting, you subtract that from the original w row. So we are adding here these two, and we get here 0. 35 minus 2 is 33m minus 60m plus 15m minus 15m minus m 0 m m and 350m. This will be subtracting from the original w row, which is you see here 1, 10, 20, 5, minus 5 and so on. So if we make those changes, like if we subtract from 1 this 0, you will be getting, let me change the color. So 1 minus 0, that is this 1 minus this 0 is 1. Then this 10 minus this 33m is 10 minus 33m. Then 20 minus 60m will be 20 plus 60m. Then 5 minus 15m will be 5 minus 15m. Then next is minus 5 minus of 15m, so 5 plus 15m. Then for S1 you have 0 and minus m, so it becomes plus m. Then for S2 you have 0, then this m minus this m gives you 0. The same way this m minus this m is 0, and finally you have 0 minus 350 m, so minus 350 m. So just replace the W line by this line, that is, instead of 1, 10, 10, 25 minus 5, 0, 0, m 0, we will be putting 1, 10 minus 33 m, 20 plus 60 m, and this way it is now our initial basic feasible solution table. You can see in the objective function line the coefficients of the three basic variables, that is coefficient of a1 is 0, coefficient of a2 is 0, coefficient of s2 is also 0, and right hand side values for the constants are all positive. So this is a feasible table. So this is initial basic feasible solution table. To check whether this is optimum or not, you will be checking in the objective function line whether there is any negative coefficient or not. Now you can notice here that 10 minus 33m is negative, and also 5 minus 15m is negative. Which one of the two will enter the basis? The most negative coefficient, and out of these two, since m is very high, we straight away see the coefficient of m if it is negative. So 10 minus 33m is more negative than 5 minus 15m. Actually 10 minus 33m will be more negative than even minus 50,000 minus 15m. The most important point will be the coefficient of m in that. So this is the entering variable, that is x1 with 10 minus 33m coefficient, that is x1 will be entering the basis, and to find out which one will be leaving the basis, you will have to divide right hand side values by pivot column values. So you get 200 divided by 35 from the A1 line, and from S2 line you get 400 divided by 10, and for A2 line, since the coefficient is minus 2, we don't use negative coefficient or zero coefficient for the division, because it indicates, negative value indicates that the raw material is actually a byproduct, it is not being consumed in the production of that product. And if the coefficient is 0, obviously there is no requirement of that resource in that product, so the possibility of that resource getting exhausted doesn't exist. So we take only from the pivot column values which are positive. So we divide 200 by 35 and 400 by 10, and we take the minimum of the two quotients, and as you can see that the minimum will be this one. So in the iteration, A1 will be the leaving variable. So the table, when you will be preparing for simplex iteration, there x1 will come inside the basis and A1 will leave the basis. You will do the iteration the same way as we did in the previous video, and we will keep on doing the optimality check. We get the optimum solution when in the objective function line there is no negative coefficient, and by putting big M here, we have taken care that once A1 leaves the basis, it will never come back, because M is very high, and this cannot become negative in future. Even in the optimum solution, if you find that artificial variable exists, then that gives us the conclusion that the original problem doesn't have any feasible solution, because it is necessary to have a feasible solution that in the basis artificial variable doesn't remain finally. So it is necessary that these artificial variables leave the basis during iteration. If they don't leave, you can conclude that the problem is infeasible and there is no feasible solution existing.